In this example, now we have a truss structure. All the members are trusses, and again, we will use the same logic, same principle to analyze this indeterminate truss. So let me give the labels. This is point A, point B, point C, point D, and finally we have point E here. And we have a point load applied to point E. It doesn't matter if you have a truss structure, a frame structure, or a combined structure. Again, we do discretization. The logic is always the same. Let's first simplify the structure. Member AE, so I have a node here, node E. Member EC, member EB, and member ED. Now, since this is a truss structure, I don't worry about the rotation. I got only translation in the vertical direction at node E and translation in the horizontal direction at node E. So we got 2 degrees of freedoms, 5 nodes, 4 members, 2 degrees of freedom, 5 nodes, 4 members. I didn't draw these nodes, but let's also show them. So we got these 4 additional nodes. So 5 nodes, 4 members, and we got only 2 degrees of freedoms. And here, of course, by its nature, we don't have any member loading. All the nodes must be joint loads and applied to the nodes. That's the definition of a truss structure. So basically, all the nodes here will be an unbalanced force for us. And if we do determine the force vector, I don't have to do superposition because I can directly obtain what the unbalanced forces are. We don't have any fixed end forces. So we have at node E, I'll just draw node E, or let's draw the whole structure. So this is the structure we have. I don't show hinges. We all know that this is all the members are truss members. So this is 100 kilonewton. If I divide it into components in the vertical direction, I got 100 times sine 30, and in the horizontal direction 100 times cosine 30. So the force vector for this case, the force corresponding or in the direction of D1 is 100 sine 30. They're in the opposite direction. So this is minus 50 kilonewtons. In the horizontal direction or in the direction of D2, I got 100 cosine 30, the opposite direction, and this one is 86.6 minus 86.6 kilonewtons. Now we obtained the force vector. Now let's see how we can determine the stiffness matrix. Nothing changes actually. So case 1, we give a unit translation in D1 direction. D1 is equal to 1 and D2 is equal to 0. That's our first case. Now let's draw the free body diagram. Node E. Now I'm applying K11 to create a unit translation in the vertical direction, and I apply K21. Sorry, let me write it in a better way. So K21 to keep the horizontal translation equal to 0. So with these given loads, I have a unit translation here that's equal to 1, 1, no bending. So this is the deformed shape of the first truss member, deformed shape of the second truss member. So this is also 1, that's also 1. So that's the deformed shape. Now, what we need to do is for this given deformed shape, we have to calculate the forces. Okay. Now, if we take a look at member AE, so it moves in the transverse direction. So by definition, if the translation is in the transverse direction, it doesn't cause any shortening or elongation. So this is our main assumption. So in order to have a shortening or elongation, the translation or the deformation must be along the element axis. So the vertical translation or the transverse translation doesn't cause any elongation. Since this is a truss member, we don't see any bending resistance. So no force on this one. And likewise, I don't see any force on this one. So only resistance in the vertical direction will come from member BE and member DE. It moves in the upward direction, but the element axis is this axis, is like that. So I have to figure out how much elongation I get if this point moves 1 in the positive y direction. So in order to determine that, let's draw a figure here. So what I'm interested is, this is the transverse translation. So this one has a transverse component as well as a component along the element axis. So that's the displacement that I'm looking for. I call it delta 1. Delta 1 will cause elongation, and delta 1, because of delta 1, we will see some axial force on this member. The same thing holds for member DE. It moves in the upward direction in unity. So if I divide it into its components, this is the transverse component of 1, and this is the component along the element axis, and that's delta 2. So if I call this angle as alpha and this angle as beta, then from geometry, draw a line, draw a line like that here and another line like that. We find out that this angle is alpha and that angle is beta. So from that, delta 1 will be equal to 1 times sine alpha, and delta 2 is equal to 1 times sine beta. So this alpha 1 and alpha 2 will create an axial force on this member. Okay. Now, when I look at these translations to delta 1 and delta 2, I see that this member elongates. So the tensile force will cause elongation. So because of this elongation, at member BE, I have a tensile force. I call it TEB. And likewise, I have a tensile force at member DE. So let's show it this way. That's all. TED. Okay. Now transfer these forces to the nodes. Let me use a different color so that we'll see. So I have TEB in this direction, TED in this direction. this one is TED. Now first, let's calculate the magnitude of what TEB is. So TEB is equal to EA over LEB multiplied by the amount of elongation, which is equal to sine alpha. TED is again EA over LED multiplied by sine beta. Okay. Now, we determined the magnitudes of these axial forces on members. Now we need to take a look at this node now. And from this node, I should determine the values of K11 and K21. So in order to calculate K11, I need the vertical component of TEB. And the vertical component of TEB is equal to TEB times sine alpha. And the vertical component of TEB is equal to TEB times sine beta. So if I write what I just set down, so we have K11 is equal to TEB times sine alpha plus TED times sine beta. So put what I just write here, put these two into that equation. So at the end of the day, what we get is as follows. I got EA over LEB multiplied by sine square alpha plus EA over LED multiplied by sine square beta. So in order to determine, or before that, let's put the values in its places and determine what that value is. And when you do the calculation, you obtain this one as 3796.82. Now let's calculate K21. So for K21, I have to determine the horizontal components of these two. And K21 will be equal to the horizontal component of TEB minus the horizontal component of TED. And in order to determine the horizontal components of these forces, I have to multiply them with the cosine of these two angles. So in that case, this one will be equal to TEB times cosine alpha minus TED times cosine beta. Now put these two equations into here, and we have TEB sine alpha cosine alpha minus TED sine alpha cosine alpha. And when we evaluate that, we obtain this value as 400 minus 436.82. So as you see, it doesn't matter if it's a truss structure. We apply the same logic. We applied K11 to create a unit translation in the vertical direction, and K21 to keep the horizontal translation equal to 0. And then we go member by member and try to figure out the forces due to that deformed shape. And these are the first column of the stiffness matrix. Now we will repeat the same procedure for the second case. So case 2, this one, D1 is equal to 0, D2 is equal to 1. Let's draw the free body diagram now. So member AE, node E. Now I'm applying K22. This will create a unit horizontal translation. And I apply K12 to keep the vertical translation equal to 0. Now let's see how the deformed shape looks. So we have a unit translation here, an elongation at member AE, shortening at member EC. This point moved by a unit amount in this direction, unit in this direction. So the deformed shape of these two members will look like this. And let's remember, this is alpha, and this is beta. So what I need to do is to calculate this is the transverse component of the translation, and this is the translation along the members direction. So for me, this is alpha 1, and for this one is the translation along the member axis, the translation along the transverse direction, and this is delta 2. And from geometry, again, we find out that this angle is equal to alpha, and here this angle is equal to beta. So in that case, delta 1 will be equal to 1 times cosine alpha, and delta 2 is equal to 1 times cosine beta. So I have an elongation at member BE and a shortening at member ED. Now let's calculate the forces. So TEB is equal to EA divided by LEB multiplied by cosine alpha, and I have compression, but I'll just call it again TED is equal to EA over LED multiplied by cosine beta. So let's show the forces. So this is tensile force, this is TED. So we have a compressive force here in this direction. So this should be TEB, this should be TED. Now here we see elongation, so that force is TAE, and here I see a shortening, that force is TEC. So transfer all these forces to the nodes. I have a force like that in this direction, force in this direction, another force in this direction, and the fourth force coming in this direction. Now we can determine what the forces are. So in order to determine what K22 is, I have to calculate the horizontal component of TEB, and the horizontal component of TEB, if you think that this angle is alpha, is equal to TEB times cosine alpha. And the horizontal component of ED, TED, is again TED times cosine alpha. So if I want to calculate K22 is I got TAE plus TEC plus TEB times cosine alpha plus TED times cosine alpha. So if I put the equations, these two TEB and TED values in its place, so I got this. I have EA over L EAE plus EA over L EC plus EA over LEB multiplied by cosine square alpha plus EA over LED multiplied by cosine square beta. So this should be beta. So when you evaluate that, we find out this value to be equal to 16,583.7. You can calculate K12 also, but if you do it, you find exactly the same number. Let's check that out. Now, K12 should be equal to TEB times sine alpha minus TED times sine alpha. So if you multiply it with these values and put it into the equation, you get exactly the same equation here, and your K12 value will be equal to this one, 400 and minus 436.82. So now, since we obtained everything, we can actually do the solution. So let me erase this part, and I'll do the solution in here, and then we will recover the membrane forces. Okay. Now, solution. So the equation that we are going to solve is again K times U is equal to F. So our stiffness matrix is like that, 3,796.82 minus 436.82 and this one is 16,583.7, and I got D1 vertical translation, D2 is the horizontal translation, and that should give me the unbalanced forces minus 50 minus 86.6. So these are the two equilibrium equations that we need, and when you solve it, we obtain D1 as equal to minus 1.4 times 10 to the power minus 2 meter, and D2 as equal to minus 5.586 times 10 to the power minus 3 meters. So these are the values of the degrees of freedoms. Now let's recover the member end forces. So this is D1 and D2. So let me erase this part and write in here member end forces. So I will calculate the member end forces for member EB. So let's draw it. This is member EB. So this point moves in the downward direction and magnitude is minus 1.4 times 10 to the power minus 2 meters, and it also moves in the horizontal direction and magnitude is minus 5.586 times 10 to the power minus 3 meters. So there are two options here. The first option is you can determine the components of this displacement along the member axis from the geometry and multiply it by EA over L. That will directly give you the axial force on this member. The other option is, again, we can use the stiffness approach. We can say that FAEB is the stiffness coefficients that we find in these free body diagrams multiplied with the member end displacements. So what is KEB? Let's determine that. So for that, we will be looking at these free body diagram, the components of this force in here and the component of the force in here. So the first case, when we have a unit translation, the contribution of this member is equal to TEB times sine alpha. This one, TEB times sine alpha multiplied by D1 plus TEB times cosine alpha multiplied by D2. So this is the equation that we are going to write. So TEB times sine alpha is equal to EA over L sine square alpha. TEB times cosine alpha, I didn't write it here, but TEB times sine alpha, I should multiply it with the sine alpha, will give me TEB times sine alpha and cosine alpha. So I have EA over LEB multiplied by sine square alpha, and here I got EA over LEB multiplied by sine alpha cosine alpha, and that's the first equilibrium equation for member EB. The second one, so we will be looking at the horizontal component of this force. So here TEB times cosine alpha plus TEB times the horizontal components we are looking at. Sorry for that. So TEB times cosine alpha will be the contribution in the horizontal direction. And here again, TEB times cosine alpha will be the contribution of this force in the horizontal direction. So when you put the equations in its place, I got EA over LEB sine alpha cosine alpha, and here EA over LEB times cosine square alpha will be the stiffness matrix for me. And if I put all the equation in its place, let me erase all this part. I have FEB equal to, the stiffness matrix has a form like this: 1920, 1920, 2560 will be my stiffness matrix. The displacements minus 1.4 times 10 to the power minus 2 minus 5.586 times 10 to the power minus 3. And when you evaluate that, the forces that we obtain is minus 30.85 in the vertical direction, minus 41.18 in the horizontal direction. So I have 30.85 in the vertical, 41.18 in the horizontal. So the resultant, let's call it FEB, is equal to the resultant of it, 30.85 squared plus 41.18 squared, and the result will be 51.45 kilonewtons, and it will be a compressive force. So in this example, yes, even though we are solving a truss problem, we apply the same logic, same approach, give a unit translation to each degrees of freedom, obtain the stiffness matrix, then you can directly obtain the force vector, and from it obtain the displacements. Then use the stiffness approach to calculate the member end forces.